To Architecture 348 and 548, Structural Technology and Practice module. In the next 5 weeks, we'll be looking at structural materials instead of structural systems, talking both about why we might decide to use one material over another, in particular, the benefits and drawbacks to using steel, timber, and concrete, and when those materials are most appropriate, when we might have decisions to make that trade off things like cost, time, form, things like this. We'll look also at those materials in detail, at the kind of quirks that each of those materials have, how we design differently for structures that are in concrete versus structures that are in steel, etc. So those three materials will form the first couple weeks of the class. And we'll do some design work, we'll do some analysis work, we'll do lots of case studies, of course, and we'll ask you both to design some structures in these materials, but also to analyze buildings that you may know or that you may be able to research anyway, to look at when steel, concrete, timber get used in certain applications versus others. And then in the last couple of weeks, we'll transition to looking at a very particular structural type, high-rises, and the particular problems that we get into, especially with lateral stability, when we're talking about stacking floors and floors on top of one another. Structural design is important, as we know, because when we're making decisions about materials and systems, we generally have to make these very early in the process. And the cost that is associated with those decisions really gets decided in the first sort of 15 or 20% of the design phase. So when we make a structural decision in pre-design or schematic design, we're stuck with that more or less for the rest of the project because so much gets associated with how the structure lays out. The problem, of course, is that our knowledge about that structure only increases as we and our structural engineers get into the sort of nuts and bolts. So the more we know going in about the benefits, the drawbacks of individual systems or materials or structural types, the more likely we are to make good decisions that will benefit our clients, both in terms of suitability, structures and materials that will be beneficial to the uses that they desire out of what we're designing for them, but also in terms of cost, that we can make the smarter decisions we can make in the first 20% of the project, the more impactful, the more effective they will be as the project moves through its various phases. We've talked in our coursework so far a lot about structural behavior and form, and we've looked at structural types based essentially on the shape that they take. So section-resistant structures that rely on the kind of cross-sectional area or distribution of that area. Form-resistant structures where we're looking at funicular patterns, funicular shapes, the way that structures hold loads in pure tension or pure compression. And more exotic things like surface-resistant structures, domes, shells, things like that, that actually use the three-dimensional double curvature of structures to carry loads, not across their sections or along their axes, but rather across their whole surfaces. These are all very good to know as architects and designers, but they're all fairly abstract, and only occasionally have we gone in and talked about the actual material and whether the material matters or not. And of course it does. Different materials have different allowable stresses, they have different strengths, they have different resistance to deflection. And so we have to think not only about whether the form is suitable for what we want to do, but we also have to think about whether the material is strong enough, whether the material deflects too much or within the bounds that we want. And as we get into these three primary structural materials, we'll talk a lot about a whole host of other considerations that we have. So not just whether the material is strong and stiff enough, but whether it's available, whether it's expensive, how it gets made, and how we can shape or form it into the configurations and the components we need. What its impact is both on fabrication time in other words, time before something shows up on site, and also in terms of actual construction time, how much time and effort one material or another is going to actually take on the job site itself. We talked a lot in previous classes about structural categories, and in particular these four. And these are important to understand the kind of overall mechanics of a structure. So again, form-active structures rely generally on kind of longitudinal axes. We look at funicular shapes, catenary shapes, and we're dealing generally with fairly simple axially loaded elements. So cables, arches, slightly more complex three-dimensional situations where we'll be looking at certain families of tents and membranes. We've looked very briefly at vector-active structures, so trusses that rely on a kind of network of triangulation of nodes and chords that fix those nodes into triangular geometries to show how this network balances external forces with internal stresses to achieve usually spanning capacity, trusses and in 3 dimensions space frames. Vector-active structures kind of lead us to section-resistant structures or solid elements, beams, girders, joists, where we're again reliant on the distribution of cross-sectional area to carry a load. So a flange on top, flange on the bottom, that can each carry compression and tension, and then a web in between that establishes or assures us of a kind of fixed geometrical relationship between these two that takes up the shear forces between them, and that combination making a sort of hybrid element that again can span, now instead of using a network of triangles, using a very, very complex flow of forces through a section. And then finally, the kind of exotic ones, shells, membranes, pneumatics, things that are surface resistant, that carry loads along their surfaces, either in this example, a singly curved vault that then has to be held to that shape, or more efficiently, a doubly curved shell that uses the principles of double curvature like an eggshell to make sure that that structure holds its shape even under loading. Again, all of these are important to understand, but they're all very abstract, and we think about them and how they operate, in most cases, before we come to the decision about what material we're going to actually use for them. So just examples of these, form-active structures where we're looking at tents or pneumatics, but more simply when we're looking at arches or cable structures, where we're reliant on simple axial flows, so membranes obviously always in tension, cables always in tension, arches or shells always in compression, never taking bending in form-active structures. Vector-active structures where we're looking again at triangulation to achieve a structural shape, and these may be hybrids. So on the bottom here we have a structure that is clearly, if you sort of zoom out and squint at it, working like an arch. If you get in very close, you realize that it's actually working like a truss that's bent around a very effective arch shape. And in these charts, you can see that we have some general rules of thumb for how far systems like this can span. So you see here we've got truss systems that can go from sort of 6 or 7 meters all the way up to 300 or 400 meters when we're talking about trusses that are kind of bent around an arch shape and then rotated around to kind of hybridize both the truss with the arch section and then the double curvature of a dome. And the more we kind of hybridize and layer these together, the greater the efficiencies we get, the longer we can span. Note that in both of these cases, the form-active and the vector-active examples here, we're talking about a very particular type called a long span, and we'll talk in more detail about long span in the next class. But these are not multi-story structures. These are programs that have very large open volumes that require a great deal of both horizontal span, but also usually a great deal of height. And notice that in neither of these cases are we stacking floors on top of one another. These are very, very specific programmatic cases where we're literally trying to make one story but we're trying to make one really, really big story. And so we have all of these specialized structural types that help us to achieve these long span, high volume spaces like aircraft hangars, or in the case here on the top, a museum where there's a desire for complete flexibility in floor planning, right? No columns, lots of high space in between the walls. Most of the projects that we'll be working on as architects, though, won't be quite that exotic, or will have structural considerations that aren't maybe quite so heroic, that are more kind of day to day. And we'll be looking instead at section active structures, beams that are spanning maybe 5, 10, 15 meters instead of 200 or 300 meters. Importantly, section active structures, because they are kind of compact, we can use these for multi-story buildings in ways that we typically can't use some of the other structural types that we've talked about. We can stack beams and girders and slabs on top of each other 8, 9, 10 times without worrying too much about the height that the structural element itself actually takes. Right? We don't build multi-story buildings out of domes, because a dome relies on the height of its section to carry the load. So right away we lose all sorts of headroom if we think about trying to build a multi-story building out of domes. If, however, we're building a multi-story structure out of beams, then we're usually talking about a rule of thumb that is about span over 16 for the beam's depth. And that's a very, very efficient number, and it allows us to put more floors on top of one another without losing a lot of head height. So we can see that just in terms of structural types, when we're thinking about functional types, whether we need one really big span or whether we're putting lots of structural elements on top of one another, we're already starting to make value decisions about what sort of structural strategy we're going to use. Section active structures, not the most exotic, not the most impressive. Very rarely are you going to get a cover shot that is of a beam just doing its job. But they're more efficient in ways that let us do this particular structural type of multi-story much, much better than some of the other ones. And finally, here, like the most exotic one, surface active, right, where we're talking about elements that really, again, use the height of the element itself. So the difference in section between, in the upper left, the footings of that shell and the height of that shell, the space between those allows for curvature in two directions that makes it a very, very efficient single span, lots of volume for very little material, not so good for, say, a parking garage, right, or an office building. And again, we'll be using surface active structures in cases where we're not worried about head height, where we've got plenty of space above us and we're really trying to make a big volume space, right? Something that has a lot of height and a lot of span to it and isn't necessarily going to be stacked one on top of the other. We think too about the way that these structures sort of instill architectural or functional patterns to the spaces that we're designing. So even if we're thinking about sort of fairly straightforward section active structures, beams, girders, slabs, we have a number of kind of subtypes where we might be thinking about the spaces that we're trying to put into those floors and whether those spaces can operate on a kind of square pattern, in which case we might put in a 30 foot by 30 foot column grid and expect either a flat slab or kind of a load joist system to fill us in, or whether they need a slightly different pattern. So a factory maybe where we have large scale equipment, but we need to put it on 2 or 3 different floors. We might be looking instead at what we call one-way systems. So we might have shear walls or bearing walls on the outside, as you see on the top. We might have relatively either thick slabs or relatively deep girders that are spanning in that single direction, right, to accommodate not necessarily a long span high volume, but a span that is bigger than the sort of typical 20 to 30 feet we might get with a slightly less exotic system. Which way that structural grain goes, what the pattern of the structural grain is, what the size of a beam or girder versus the size of a column versus the size of a slab. All of these are things that we want to think about early in the design process, right? That first 20% of a typical design project. And we want to integrate that as much as possible with what we know about our client's program so that we're specifying and developing a structural system that works well with the desired function of the spaces that it will surround. As the design moves forward, we find that there are a huge number of constraints or influences that are going to both sort of tell us what we can and can't use as a system, and also that are going to suggest refinements to that system, ways that that system develops around some of these constraints. So very obviously, when we get a site, we might be looking at whether that site has a slope to it, whether the soil of the site can carry heavy loads or not. We will be looking at things like wind forces on a structure, whether we have hurricane or tornado force winds. We'll be looking at seismic considerations if we're designing in a seismic zone. We may also be looking at what our neighbors are doing, what loads those neighbors are putting on the soil and how to respond to those. We'll talk in a minute about code constraints and what drives often the choice of structural system, not based from maybe a programmatic sense, but from a fireproofing sense. And this relates both to the type of materials, it relates to the height that those materials allow us to go safely, but it can also relate to things like seismic safety, whether we can have noise coming in and out of the building, et cetera. There may be regulations that a municipality or a state or a government entity are putting on our building that forces us into some decisions about structure or not. And then we'll get into the sort of architectural considerations. So does our client want tall spaces or low spaces, long span, short span, multi-story or single story? What are the patterns of use and how do those relate to the way that a structural grid might develop? Are the bays repetitive? Are there places where we can put in systems that will allow for greater lateral stability, and how do we integrate those very solid pieces with our client's need for maybe some more open spaces? And then finally, we'll also be looking at how all of this resolves itself in the ground. If we're using a really heavy structure, then we might be surcharging the soil with more weight than it can really bear, and we might have to look at other systems. If we're, on the other hand, doing something that's really lightweight, we may have more freedom in where we put the footings, how many footings we put down, and how we collect the loads before they go into the ground. We'll look at some things that are kind of integral with the architecture, like how the structure and enclosure work together. This can lead us down paths like realizing that there are choices, environmental choices about whether the structure emerges kind of on the outside of the envelope, or whether climate considerations mean that we want to contain it all, so we're keeping all of the thermal mass within a climate-controlled envelope. We may look at the architectural considerations of repetitive modules. What happens if we solve the structural problem in one bay and it all works functionally, but when we put all those bays together, we're not maybe satisfied with the architectural outcome? What can we do to that? How loading conditions will work. So if we're in hurricane country, or even if we're tall enough that we begin to have to think seriously about the effects of wind, how do we integrate lateral stability into what we generally think of as a gravity system? And then a whole set of serviceability issues. How durable is the material? How easy is it to maintain? Can it weather, or does it need to be protected? What does it do to the spatial qualities within, to our decisions about, say, lighting or tactility or color palettes? Can we expose the material? Do we have to protect it against fire or water? Can it add to our kind of architectural palette on the inside and outside? And then things that we maybe are beginning to think about more and more. Decisions often get made based on construction limitations or on, these days, environmental limitations. We may have to meet a construction schedule that requires us to telescope some phases of the project, and there are certain materials or certain ways of getting those materials that can help with that. There are other ways that tend to stretch schedules out. We'll very often find that compressing a schedule means that things get much more expensive or have to be coordinated much more tightly. These can also influence both the material that we choose and the processes we use for getting those. There may be economic restrictions, not only on the materials themselves, but also on labor, depending on what the economy is doing at the time, depending on whether there are other big projects going on in the region. And there may be sort of regional peculiarities, right? Ways that we can get certain materials but not others. Changes in the global market that affect both where we go get our materials from and how much those materials cost. And steel is probably the greatest example of that, right? A global commodity that requires us sometimes to respond to changes maybe in the economy in China or Japan or Germany, rather than focusing just on the economics of our site in particular. And then finally, structure being by volume and weight, usually the greatest portion of a building. We want to be very careful about the embodied or embedded energy that goes into our structural components. None of the materials we'll talk about have zero impact. They all have a penalty that we would like our building to pay back over its lifetime. Of course, the lower the embodied energy we choose, or the more that our material choice can contribute to the efficient life cycle cost of the building, clearly the greater benefit that will have ecologically going forward. And finally, durability. Some materials will last much longer than others. And this we think of more and more in a kind of ecological way, right? If we design a building that really only has a useful life of 50 or 60 years, are we being as responsible? Are there other decisions that would maybe double or triple the life of that building that, even though they might not directly affect our client or our work, we think more and more about that seventh generation, right? And what decisions are we making that will impact them and the decisions they'll have to make about the legacy buildings that they get. So one of the first things that we'll look at is what we're actually allowed to build with. And we'll very often find that municipal codes or state codes, or in some cases industry-specific codes, will actually tell us what we can and can't design our structures out of. These will be based on location, occupancy, height, and area. And the goal with most of these codes is to provide a building that will safely defend its occupants against a building fire in particular. Other codes will deal with things like seismic and wind and water infiltration, but the one that influences us most is fire safety, right? Whether the structure is going to burn or whether it's going to perform well in a fire. These four elements all kind of combine. There's a kind of interplay between them that eventually will often restrict us to what we call fire-resistant materials, essentially concrete and or very carefully protected steel. The tighter the location, the more restrictive the codes typically are. If we're surrounded by other buildings, we have to worry not only about our own structure in a fire, but whether other structures burning need to be defended against for our occupants. What that occupancy is important. If we're designing a high hazard facility, something where there's a lot of chemistry or a lot of volatile materials, we'll obviously be more restricted about what we can build with. Building height becomes important because it takes time and it takes space to get people from upper floors out of a tall building in an emergency. And so when we have a taller and taller building, the codes will tell us that that building needs to be made more and more safe, and it needs to focus on containing fires within floors or within spaces on floors, and giving occupants time to get out, giving firefighters time to come in and get up to the level of the fire. And then overall area. We never want to put too much flammable material in one contiguous volume. And so again, depending on whether we're warehousing things or whether we have maybe a kind of simpler or lower fuel load occupancy, we might be allowed much more space than if we're designing a very tightly filled area. You can see on the right occupancy classifications. These hopefully you're familiar with from your course work on building codes. But you can imagine each one of these has a different kind of concern when it comes to fire. So assembly, we're mostly worried about getting people out. Factory and industrial, however, we're more worried about containing a really volatile, flammable material, or in some cases containing what could be actually an explosion. Institutional, so hospitals, nursing homes, we're worried about being able to give places of refuge to people who may not be quite so mobile. And educational business, we're worried about kind of high loads of people that we want to protect, we want to separate from any danger and give them time to exit. The material of the building structure is impacted by all of these, and codes will always prefer a more fire-resistant material for more dangerous occupancies, for more restricted locations, for taller building height, or for larger overall area. So what do these look like? Well, in general, we have 5 types of construction, 5 types of structural materials. The one that we will use for the biggest projects, the most kind of dangerous projects, high rises, but also things like warehouses, especially for volatile materials, will be concrete and steel. And if we have what's called a type 1, then pretty much every structural element, columns, walls, floors, will all need to be made of either concrete or steel. So no flammable materials anywhere in the structure itself. Partitions, doors, furniture, fixtures, those could be of flammable materials, so timber, but will very often have to compartmentalize so that what we call the fuel load won't get too great in any one space. We have a kind of reduction of that in what we call type 2, where some of those structural elements, walls, floors, etc., could be something like timber. Usually will be a little bit more restricted in area and in height. And as we go down the list, you can see that we have what's called non-combustible, so a material that won't contribute to the building load, or the fuel load, but that might not perform so well in a fire, so something like glass or unprotected metal panels. And then type 4, type 5, type 4 is heavy timber, so large-scale timber elements that will char instead of burn. And type 5 is kind of typical residential construction, so wood studs that, as we know, can go up very quickly in a fire, but here we'll have such a small area or such a small height that we're happy that the small number of occupants in, say, a single-family home could get out fairly easily. We do see type 4 and type 5 often allowed up to sort of 4 or 5 stories in apartment buildings. And of course, today one of the big issues is finding ways to make timber a renewable resource, a lightweight structural material, something we'd like to be able to use more, finding ways to make timber safe in a building fire so that we can actually use type 4 for taller and taller buildings with bigger and bigger area. And as you can see in the bottom, one of the ways that we do this is we use both passive and active fire protection. So passive fire protection, insulation around a vulnerable material. We're used to seeing this with steel, but we'll see it more and more probably with timber. Active fire protection, where we're using sprinklers to suppress a fire before it endangers any of the vulnerable structural elements that we may have designed. What those types allow in a typical code, so here from the International Building Code, you can see that as we kind of go down in the construction type to the more vulnerable materials in type 4 and type 5, you can see that we have restrictions on both height and area. So if we have a concrete or a protected steel building where every structural element is fire rated, you can see on the left that for certain occupancies we have UL for unlimited, right? Unlimited height, unlimited number of stories, unlimited floor areas. We regard concrete and protected steel as essentially completely safe. The second we start making structures out of materials vulnerable to fire, you can see that we very quickly have pretty onerous restrictions. And these go all the way down, as you can see in type 5, if we're just dealing with stud construction. These can get very small, right? 40 feet tall, 1 or 2 or 3 stories, maybe a little bit more for residential, very, very small floor areas to make sure that people can get out in a hurry and that we're not endangering either large numbers of people or really large areas by making the building structure actually flammable. The way that we do this, as you've seen in your code coursework so far, is that we have what are called fire ratings. And usually type 1 construction will rely on fire ratings of 2 to 3 hours. So as you can see here, structural frame, bearing walls, floor construction, and roof construction, these all have pretty onerous considerations, right? This means that in a type 1A structure, our structural frame has to survive a fire for 3 hours, which is usually, of course, going to be more than enough time for firefighters to arrive and extinguish the fire. But that's how seriously the code takes this, that a 3-hour fire rating is required for a structural frame. You can imagine why, right? That's the last thing in the world that you want to fail in the event of a fire, because then you not only have the hazard of the fire itself, you have the hazard of the structure actually collapsing. If you look down, you can see that non-bearing exterior walls have an additional consideration, which is that we're not so worried about the exterior wall either containing the fire or resisting a fire if it is set back far enough from either a lot line or the center line of a street or a line between 2 buildings on the same property that we can control. And the idea there is that a fire is very unlikely to jump 20, 30, 40 feet out from one building and impact another. It may damage that exterior wall, but it's not likely to ignite anything within the next building. This is an innovation that you can imagine came around when the curtain wall began to be a popular device in the 1950s, when we stopped making the exterior walls of tall buildings out of bearing walls and started making them out of these thin glass skins. There was a lot of agitation to allow the codes to kind of relax. And you can see that effect here where all of the elements, all the kind of structural elements of a type 1 building have these very onerous restrictions, except for that exterior wall. And that is going to be based on where it is relative to a street or where it is relative to any neighbors. As you go down, you can see that the restrictions kind of tail off as we get through type 2, 3, 4, and 5. Type 5, you can see a type 5B construction basically has no fire resistance at all, right? This would be for like a detached garage or a shed or something. Otherwise, we need to have that kind of one layer of gypsum or something even protecting stud walls, right, to give us some chance of getting out of a building that's on fire. Down below, you can see some of the ways that we protect or some of the ways that we achieve really, really high fire resistance ratings. So a type 1 construction is usually going to be either a steel column that is embedded in lightweight concrete or surrounded by gypsum wallboard, vermiculite, spray-on fireproofing. And you can see there that we can get anywhere from 1 to 4 hours fairly easily. Reinforced concrete, in other words, if you just kind of reverse the proportions and use heavyweight concrete for the structure and you have steel reinforcing that has at least an inch of covering, you can see that very easily you can get to a 1 to 4 hour rating with that as well. So type 1 is almost always going to be a protected steel or concrete. Types 2 and 3, we might have some steel that is unprotected. Type 4 is usually heavy timber, and then type 5 can be anything, right? And usually we'll use something really cheap like lightweight studs if we're only needing to get a type 5 rating. So as we're considering a structural material based on code, we will look at the group occupancy. We will usually read over in the code until we find a description that matches what we need in terms of story height, in terms of number of floors, and in terms of allowable area. And when we hit that, we will read up and we will find out what type of code, or what type of structure the code will allow us to build with. Of course, we can choose something more robust, more fire resistant, but we can't choose anything less fire resistant. And this again will come, in this case, from International Building Code, looking up the group, reading over and seeing where our kind of the size of our building, both in terms of height and area, comes, and then reading up, and then going to the definitions and seeing what a type 3 will and won't allow. We have a lot of other considerations, though, that we'll have to think of, and this is where we get into the kind of quirks of each material, right? From wood and masonry, which is generally kind of locally produced, kind of hand crafted, steel, which is often purchased from overseas in America today, fabricated in a shop, driven to the site. Site cast concrete, often a local industry that uses maybe imported cement, but local aggregate, but requires carpenters for formwork and requires time for setting. And then precast concrete, which is, of course, formed not on site by formwork, but in a factory. As you read down this set of design criteria, you see some things very quickly, and particularly the kind of choice between steel and concrete, right? This is the one that we'll most frequently make, because very often we'll get told by the code that we can't use timber, say, for a high-rise structure. We can't use lightweight timber for a high-rise structure. So you can see that site cast concrete has great fire resistance, as does precast. We can, in some cases, use it to achieve kind of more radical or less regular form than steel or precast. You see that we minimize off-site fabrication time. We don't need to do a whole lot before we start on the job site. And for a 4 to 20-story building, site cast or precast concrete is relatively efficient. It also allows us to create monolithic structures, so we don't need as much in the way of shear walls or lateral resistance. If then you look down the list of steel, you can see when we might use steel instead of concrete. For example, steel we can assemble under adverse weather conditions. We cannot pour concrete when it is too cold or sometimes too hot, or when it rains and there's too much humidity in the air. Steel, on the other hand, we can assemble almost no matter what's going on outside. Steel is quick. We minimize our on-site erection time. We also, for a low building, minimize construction time, right? If it's a 1 or 2 story building, then steel is often going to be much quicker than concrete. 4 to 20 story building, it's maybe a little mixed. And you can see, too, that we're certainly not minimizing off-site fabrication time, right? Steel takes a long time to get sourced, and then because we have to design all of the fittings, all of the connections to be done in the shop or to be accommodated in the shop, we need time for the fabricators to actually put the material together. We make up for that often in on-site erection time. Notice that steel is lightweight, so if we have crummy soil, we may find that we want our structure to be as light as possible. There are other kind of trade-offs that we have. Steel tends to be much more expensive as a material cost than concrete because it's so kind of finely worked. Concrete, on the other hand, often needs much more labor and much more skilled labor. Steel will put together just with iron workers. Concrete will have carpenters who have to build the formwork, and then we'll have concrete workers who actually pour and then finish the concrete. Different sets of skills, different sets of construction labor, often subject to very, very different costs depending on what's going on in the economy around us. We'll then often make decisions based on the spans that we're looking for. And here you can see a kind of basic logarithmic span range where you can see our sort of exotic long span structures like domes and cable stayed suspensions, right? Those are all single story structures. When you look down at the things that we make multi-story buildings out of, so light floor trusses, joists, decking, beams, what you see is that we have some advantages with steel and concrete, but that these two are kind of in the same range. And even timber, if we treat it right, especially if we use something like glue lams, they're all basically competitive in terms of the span. We can get slightly bigger spans with steel, especially if we use open web joists. But between concrete, sort of less exotic steel items, and timber, we're all within that sort of 20 to 30 foot range. Wood we'll often use for residential because it's so much cheaper, right? You can see that joists will span any sort of typical residential dimension up to 17 or 18 feet. The other thing that we might look at is live loads. So depending on what type of occupancy, you can see that those will have very, very different loads. So manufacturing, warehousing, anything where we're putting vehicular loads, you can see that we might have between 150 and 250 pounds per square foot. Generally, for most architectural considerations, will be in what we call medium loads. So you can see if they're assembly, lightweight, sort of car garages, hotels, libraries, things like this, will be in that sort of 60 to 100 pounds per square foot load. One thing that violates this is library stacks. For putting a lot of books together, you can see that it will have a much, much heavier load. And all of these will influence possibly what we want to use for our structural system. So here you can see that some of this is really intuitive, right? Platform or timber frame we're used to in residential construction where we have very light loads. You can see that we start to get restricted when we get to very heavy loads. So anything that's vehicular, manufacturing, sort of heavyweight storage, we're going to have certain types of construction, lightweight steel, rigid steel frames, two-way flat plates, things like that, where we're no longer able to use every structural type that we can think of. Instead, heavier, very heavy loads will restrict our palette just a little bit. You can see too that some of the more exotic systems are not so good for light loads. Not that they can't carry them, but that they're overkill, right? Overly expensive for the kind of residential loads that we might have. So you will rarely see, for example, a two-way beam and slab used for residential construction unless it's something that is architecturally called for. That's an expensive way to build a concrete system, and so it'll be reserved usually for manufacturing or for automobile purposes. These decisions are important because, as you can see, if you count our foundation and substructure and superstructure, we are roughly about maybe a fifth to a quarter, in some cases up to maybe 40% of the cost of a building, right? Of the construction cost of a structure. Not so much once we're done in terms of the operation, but that investment in material and in labor to make all of the kind of beams and columns and slabs, especially of a multi-story building, is a significant piece of the construction cost. Anything that doesn't go into the structure, we can end up using for something else. So the nice finishes that we want for interior construction, the kind of more efficient HVAC system, the better lighting that we want to show off the spaces inside better. There will be this kind of battle between all of these specialties. And we, of course, will be trying to push for less and less expensive structural systems, foundation systems, maybe mechanical and plumbing systems, so that we can have a larger budget for the things that we value. There will be push and pull, of course, on any project, and we'll end up often kind of arguing with our engineers or our consultants about how this money gets distributed. But any way that we can make structure especially more efficient, means that there will be more cash, essentially more budget, for some of the things that we really value. And the way that this kind of works is sort of changing. We have more and more knowledge early in the process, and we put more and more of our design effort into that first 20% of the project because we have better tools now, right? With building information modeling, we can make much more informed decisions much more quickly about the impact that a structural decision especially might have on the project going forward. If we're able to make good decisions in preliminary design and in detailed design, with building information modeling these days we generally can, we're putting our effort where it can do the most good, right? Where it can be the smartest. No longer are we so much spending 50 or 60% of our work as architects in documentation. We're letting the software do a lot of that for us, and therefore we can really apply our kind of knowledge much earlier in the process. One thing that affects this, though, is that we may know what the structural system is, we may make decisions about the structural material, but it's very likely not going to be until after bidding, and in some cases during construction, when we first get input from the people who are actually making this stuff. And even then, when a subcontractor is finally on board for steel or carpentry or concrete, they are going to have communications, of course, up through the contractor and through the owner, but they're going to want to talk to us and they're going to want to talk to the structural engineer. And this is that problem of knowledge coming on board often only after the construction contracts are signed, right? The people who are actually putting this stuff together, bringing the knowledge of how the nuts and bolts are actually going to get put together on the site, often long after the design process. The more we can know, either from previous experience, from talking with engineers and architects who've worked in the materials that we've worked with before, the more we can anticipate what that subcontractor is going to bring to the table, what concerns they're going to have, how they might want to work, the smarter the project will be, the less expensive the project will be. Okay, that'll do it for this little bite. We'll have a second half to this first lecture where we'll look at some case studies and talk about how decisions about materials and types, but also about fabrication processes and processes on the job site itself can impact the way that we think about not just structural form, but also structural materials.